A magnitude 4.9 earthquake struck the floor of the Pacific Ocean roughly 80 to 100 miles off the southern Oregon coast, and not a single person on land felt it. No damage, no tsunami warning, no national news coverage. By every standard measure, this was nothing. Moderate earthquakes happen out there constantly. Let me walk you through exactly why and what the real, evidence-based science actually says about what this means. Let's start with where this actually happened, because location does most of the work in this story. The epicenter sits in one of the most tectonically complicated patches of ocean floor anywhere on the planet, the Blanco Fracture Zone. A roughly 350-kilometer-long transform fault system running northwest off the Oregon coast, connecting the Gorda Ridge in the south to the Juan de Fuca Ridge in the north. This is where new oceanic crust is being manufactured in real time at the spreading ridges, while simultaneously being sheared sideways along the transform fault. This region sits at the northern edge of the Gorda Plate, which is itself being driven underneath the North American continent a little farther east, at the Cascadia subduction zone. That neighborhood is loud, seismically speaking. The Mendocino Triple Junction, just to the south, is where the Pacific Plate, the North American Plate, and the Gorda Plate all meet in one place. And the USGS describes this region as one that regularly produces magnitude 6.5 and larger earthquakes. Local officials and seismologists have made this point repeatedly over the past year, as the Blanco Fracture Zone has produced a string of moderate quakes, a 5.7 in early June, a 5.5 and 3.9 pair later that month, a 4.6 and 4.2 pair more recently, and now this 4.9 against that backdrop. A 4.9 really is background noise for this particular fault system. The motion here runs sideways rather than vertically. It's what's known as a right lateral strike-slip fault. The two plates grinding past each other horizontally rather than one thrusting up over the other. That's exactly why no tsunami warning was ever issued. A sideways slip doesn't displace the water column the way a vertical thrust motion does. So why are seismologists still talking about this one? Because the question that always comes up within hours of any earthquake near this corridor is the same one. Did this push the Cascadia megathrust closer to failing? The published scientific answer, based on well-established research from the Pacific Northwest Seismic Network, is no. And the reasoning is worth walking through because it's solid physical explanation, not reassurance for its own sake. The Pacific Northwest Seismic Network has dealt with this exact question before. After events far larger than a single 4.9, including swarms along the Blanco Fracture Zone involving dozens of earthquakes, some reaching magnitude 5.5 to 5.8. The network's published conclusion in those cases was that the slip in those events was unlikely to have caused any significant changes in stress along the Cascadia subduction zone, roughly 200 kilometers closer to shore. Two reasons explain why. The first is distance. Static stress changes, the permanent mechanical nudge one earthquake delivers to surrounding rock, don't travel far. They fall off sharply with distance, roughly on the order of a few rupture lengths from the source. A magnitude 4.9 ruptures something on the order of 1 to 2 kilometers of fault. The southern Cascadia locked zone sits roughly 200 kilometers away, approximately 100 rupture lengths of separation. The stress change arriving at that distance isn't small. It's functionally zero. The second reason is the rock itself. The crust out at a spreading ridge like the Gorda Ridge is brand new and geologically young. Young oceanic crust at a spreading center is hot and behaves fundamentally differently than older, colder, stiffer rock. Seismologists studying this region have used an analogy that's become one of the most cited explanations in Pacific Northwest seismology. It behaves like a fresh cookie just out of the oven. Push on one side and the other side barely notices, because the material absorbs energy rather than transmitting it. Research from the network has gone further, stating that even a magnitude 7.0 on the western Blanco segment would be unlikely to significantly load the subduction zone. A magnitude 4.9 releases roughly 1,000th of the energy of a magnitude 7.0. This physics is not a close call. So the 4.9 did not trigger Cascadia. What events like this reveal instead is something more interesting. How scientists actually monitor whether the Cascadia megathrust is showing any signs of change at all. Beneath the Cascadia margin, below the locked zone that will eventually break in a megathrust earthquake, the plate interface releases strain in a completely different way than a conventional earthquake. It does it through something called episodic tremor and slip, or ETS. During these episodes, the fault deep below the surface creeps along slowly over days or weeks, accompanied by a faint, continuous seismic signal called tectonic tremor. No human being has ever felt one of these events. They recur along different portions of the Cascadia margin, roughly every 8 to 22 months, depending on location. The Pacific Northwest Seismic Network tracks this tremor continuously and publicly in real time. This is the test researchers essentially run every time a moderate offshore earthquake hits this corridor. If the event had in any way meaningfully loaded or disturbed the southern Cascadia margin, one plausible signature of that would be a burst of tremor activity in the deep zone beneath southern Oregon and far northern California in the hours that followed. Checking that map rather than reacting to the magnitude number alone is standard practice in this field, and it's exactly why researchers don't panic every time a moderate quake hits the Blanco Fracture Zone. But also don't dismiss it outright without checking. Now let's talk about the bigger scientific context that makes any Cascadia-adjacent earthquake worth understanding properly. Because there's genuinely important research here that reshapes how scientists think about the worst-case scenario for this fault. In May 2026, Oregon State University announced findings by marine geologist Chris Goldfinger and a large international research team, published in the journal Geosphere, titled "Unraveling the Dance of Earthquakes: Evidence of Partial Synchronization of the Northern San Andreas Fault and Cascadia, Megathrust." The origin of this research is genuinely unusual. Back in 1999, a research cruise collecting deep-sea sediment cores off Oregon and Northern California experienced a navigational error that carried the ship roughly 55 miles south of Cape Mendocino, out of the Cascadia zone entirely and into the San Andreas fault system. They decided to drill a core there anyway. What came up didn't make sense under normal conditions. Sediment layers called turbidites, deposited by underwater landslides, normally show a predictable structure. Coarse material settles first at the bottom. Finer material settles more slowly on top. This core showed the opposite. Fine material at the bottom, coarse material above it. The team's interpretation was that the fine lower layer had been deposited by a large Cascadia earthquake, and the coarser upper layer had been laid down by a subsequent rupture on the nearby San Andreas fault, before the fine sediment from the first event had even finished settling. They called this structure a doublet, then went looking for more. Across roughly 300 years of sediment cores collected north and south of Cape Mendocino, they found a pattern that's become one of the most discussed findings in West Coast seismology in years. Cascadia turbidites over that span are closely associated in time with earthquake deposits along the northern San Andreas fault, with a time separation between them averaging about 63 years. In at least 3 instances within the past 1,500 years, including the most recent event in 1700, researchers believe the two ruptures were separated by minutes to hours, not decades. Goldfinger's own framing of what this means has circulated widely in the scientific community. We're used to hearing Cascadia described as a catastrophic, huge thing on its own, but it turns out that's not necessarily the worst-case scenario. A single Cascadia earthquake alone would draw down the emergency response resources of the entire country. If Cascadia and the northern San Andreas were to rupture together, or within hours of each other, you'd have San Francisco, Portland, Seattle, and Vancouver all simultaneously in an emergency situation within the same compressed time window. There's also newer research on the physical hazard itself. In April 2026, a team of seismologists, led by Aaron Weck, presented findings at the Seismological Society of America's annual meeting showing that the Juan de Fuca plate beneath northern Oregon's coast sits approximately 5 kilometers shallower than previous estimates had shown. Around 20 kilometers deep near the coastline rather than the 25 kilometers previously modeled. That shallower position increases the estimated peak ground acceleration during a future Cascadia megathrust earthquake by roughly 9 to 17% along the Oregon coast. The same study identified a previously uncharacterized sedimentary basin beneath Tillamook, Oregon. Sedimentary basins amplify ground shaking, the way a bowl of water shakes harder than solid ground. Together, these findings mean shaking from a future Cascadia rupture along the Oregon coast is now understood to be measurably stronger than earlier hazard assessments calculated. Now hold that context against the actual recurrence numbers because they're sobering regardless of any single earthquake this week. At least 19 great earthquakes of magnitude, 8 or larger, have ruptured most or all of the Cascadia margin in the past 10,000 years. Full margin magnitude 9 events recur on average roughly every 500 years. The southern portion of the margin, combining full and partial rupture events, sees major earthquakes on average approximately every 330 years. Bringing magnitude 7.5 and larger events into the count drops that average interval to about 233 years. The current gap since the last major rupture stands at 326 years. The paleoseismic record contains 42 identified Cascadia earthquakes over roughly 10,000 years. Narrowing to the last 4,000 years, the current interval since the last rupture exceeds approximately 95% of all recorded intervals in that span. The probability figures that follow from that math, over the next 50 years, the chance of a full margin magnitude 9 is estimated at roughly 10 to 15% on a time-dependent basis. For magnitude 8 or larger, specifically in southern Cascadia, the time-dependent probability is approximately 30%. Research from Goldfinger and colleagues, working from the offshore turbidite record, has published figures ranging from 37 to 42% over 50 years for the southern margin specifically. None of those numbers changed because of this week's 4.9. They were exactly that high the day before, and they'll be exactly that high next week. That's the genuinely uncomfortable part of this story. This moderate offshore earthquake didn't move the needle on Cascadia's underlying risk, but neither did it reveal a fault that's anywhere close to releasing the pressure it's been accumulating since the night of January 26, 1700. That's the confirmed date of the last great Cascadia rupture, established with extraordinary precision through tree ring death dates in drowned coastal ghost forests, layers of coastal land subsidence, offshore turbidite deposits, and Japanese written records of an orphan tsunami that crossed the Pacific with no local earthquake to explain. Its scholars back-calculated the travel time and arrived at a precise date. It's also worth understanding the real, practical stakes here because they're substantial. The Oregon Department of Geology and Mineral Industries has modeled the consequences of a Cascadia rupture using a nighttime scenario with lodging assumed fully occupied and coastal populations at home. Their modeling shows combined resident and visitor fatality estimates ranging from roughly 15,500 in the smallest modeled scenario to roughly 45,700 in the largest. Push the average departure time from 10 minutes to 15 minutes after shaking begins, and the largest scenario estimate rises to just over 74,000, a difference of roughly 30,000 people, with the only variable separating those numbers being 5 minutes of hesitation. That sits alongside survival research showing that anyone caught in roughly 2 meters of tsunami flow depth has only about a 1% chance of surviving it. At lower flow depths, survival odds can approach 50%. That's the hard numbers argument for knowing your tsunami evacuation route now, before you're standing on the Oregon coast with the ground shaking and roughly 15 minutes before the water arrives. So what are seismologists actually watching in the weeks ahead? 3 things, and all of them are publicly checkable in real time. First, tectonic tremor on the southern Cascadia margin. The Pacific Northwest seismic network updates its tremor map continuously. The question is whether the deep zone beneath southern Oregon and far northern California produces an episodic tremor and slip event in the coming weeks, and whether it looks routine or unusual in timing, duration, or spatial distribution. Second, activity on the inland fault systems of northern California, particularly the Bartlett Springs and Macama fault zones, which sit at the northern end of a structural chain running directly south into the most densely populated seismic corridor in the American West. That's simply what review lag looks like when the nearest instruments are hundreds of kilometers from an offshore source. As that catalog gets reviewed over the following week, the full picture typically becomes clearer. None of this is a forecast. Cascadia does not issue warnings, and the most scientifically honest position available is that this fault could remain locked and quiet for another century. Or it could rupture tomorrow. Both outcomes are completely consistent with everything the geological and seismic record currently shows. If you live on the Oregon coast, the Washington coast, or in the Northern California coastal zone, know your evacuation route. Know the ground beneath your feet. That's the one thing genuinely worth acting on today, not because this earthquake raised the risk, but because the risk was already there and now is a good moment to actually plan for it. And there is one final point worth remembering. Earthquakes do not need to be predictors of something larger to be important. Every event gives scientists another piece of information about how stress is moving through the crust, how faults interact, and how different parts of the regional fault system respond when the ground shifts. That information becomes especially valuable in a region like Cascadia, where the biggest earthquakes occur infrequently enough that no single generation gets to experience the full range of possibilities. Scientists have to combine modern instruments with older geological evidence, historical records, and patterns preserved in the landscape. For people living along the coast, the most useful response is therefore not watching every earthquake as if it were a countdown. It is building habits that work regardless of what happens next. Know which direction leads to higher ground. Know how long it would take you to reach a safe location without a car. Keep emergency supplies available. And make sure everyone in your household understands what to do if strong shaking is followed by an official tsunami warning. If the ground shakes strongly enough that you have difficulty standing, especially along the coast, don't wait for a perfect explanation before taking protective action. Strong shaking itself can be the warning that matters. Then, after the immediate danger passes, let scientists do what they do best. Collect the data, compare the signals, review the earthquake catalog, and determine whether anything about the event actually changes the scientific picture. The faults are still active. The region is still capable of producing significant earthquakes. And the instruments watching the Pacific Northwest are getting better every year at detecting even subtle changes beneath the surface. If you want to keep following this as new research and monitoring data come in, subscribe and turn on notifications.